Now coming to the mechanism of halogenation. Consider an alkene. To this alkene, let us add a halogen. Okay, bromine. Now in this, initially, as I said, attack is initiated by an electrophile. Yes, we are without the bonded pair, and now this goes off with the bonded pair. So this bromine is now in the form of Br plus, right? So when this Br minus is lost, now the bromine, Br plus gets attached to the alkene across the multiple bond to give an interesting thing. Look at this. Okay. Look at this. Bromine. But see, because see, already it will have one. This, right? All six will be there. 6 plus these two. That means, no, the bonded pair is lost, right? So that will have 4 plus these two. That means 6. So that will actually get a positive charge. Okay. Because the bonded pair is lost, then this is called cyclic bromonium ion intermediate. Cyclic bromonium ion, right? See, bromine is added across the multiple bond. Now, the other bromide enters into picture. Say this bromide, okay, take Br minus this one. Now, this bromide cannot actually enter from this area, right? From this area, it cannot enter because this is already closed. Okay, so forget about attack from that end. Now, this actually attacks from the opposite side. Now, this is what I call anti-addition. Anti-addition. Anti or anti. Okay, look at what happens. See, as and when the bromide attacks an anti-position, what happens? This immediately goes towards the positive charge. Then look at what we get. See, because of the attack of this, see the position of the things is changed. Now this is anti, right? The bromines are at anti position to each other. Okay. This is a simple mechanism. Now we know one important thing. Whenever there is anti-addition, what do we go for? Seats, car, or TAM, right? What do you mean by car? cis anti-addition racemic mixture, right? Trans anti-addition meso compound. Okay. So this is the mechanism. Now let us take an example. See, this is a cis compound, right? Because both the hydrogens are onto the same side. When treated with bromine in CCl4 solution, so according to this, cis with anti-addition, what do we get? We get a racemic mixture. Come on. You can actually go with both wedge or both dash, because both wedge, both dash in case of syn addition, and in this case, because it is anti-addition, one must be with wedge and one must be with dash, right? So let me show you that. A hydrogen, another hydrogen. So here let me add a bromine with a wedge, and here with a dash. Okay, of course, it's mirror image because we get a racemic mixture, right? Now, let me give you some clarity on this. See, because it is anti-addition, we can take it this way. One with wedge and another with a dash. Okay, look at this. Dash, then wedge. This is anti. Both with wedge, both with dash is syn. Okay. Okay. Then. Now, addition of hydrogen is done, addition of halogen is done. We'll now go for the addition of hydrogen halide. In the addition of hydrogen halide, I have two mechanisms. Electrophilic addition, or let me say ionic mechanism. And there is some other thing which goes via a free radical, a more stable free radical. So that's a free radical mechanism occurs in the presence of peroxide. Let us first go for this electrophilic addition. See in this, check this out. Now this is a symmetric alkene. Symmetric in the sense, got the same thing attached. Two hydrogens here, two hydrogens here. I mean the same atoms are same groups attached. Of course, the reagent is unsymmetric. It's not like the H2 or X2. See, these are symmetric, but this one is HX, unsymmetric. Two different. Now, when HX is added in the presence of anhydrous aluminium chloride, no problem. We can just remove a bond, add a hydrogen to this, then halogen to this. Even if it is opposite, even if it is the other way also, not an issue. We get the same product. No confusion at all. We get ethyl halide. Now the interesting point. See, when unsymmetric alkene is taken, this is unsymmetric. Hope you understand. Look at this. See, here you got two hydrogens, but here you got a hydrogen, you got a methyl group attached to the double bonded carbon. So it's unsymmetric. Unsymmetrical alkene. Now, when the unsymmetrical reagent is added to unsymmetrical alkene, that is when the interesting thing arises. Of course, we can remove a bond, but there are two possibilities. We can add a hydrogen to this, halogen to this, or even the other way also is possible. Hydrogen to this, halogen to this. Okay. Let us consider this as the first possibility and this as the second possibility. Okay, what do we get? CH3, CH. In the first possibility, we are adding X to this. Okay, this is A. Then B. See, in this we get CH3, CH2, CH2, X. You know, this is major. This, of course, is minor. We'll give you the mechanism. And say this is major according to Markovnikov rule. Okay. What is Markovnikov addition or Markovnikov addition? See, it can be given this way. When an unsymmetrical reagent is added to unsymmetrical alkene, the negative part of the reagent, here in this case it is X minus, negative part of the addendum or negative part of the reagent adds on to that double bonded carbon which has less number of hydrogens. So that is Markovnikov rule. Negative part of the reagent adds to that double bonded carbon having lesser number of hydrogen. If this one has just one hydrogen, whereas this one has two hydrogen. So it is this double bonded carbon to which X minus gets added. Okay. That is Markovnikov rule. Come on. Look at the condition. When an unsymmetrical reagent is added to an unsymmetrical alkene, negative part of the addendum, nothing but reagent, adds on to that double bonded carbon. Which has lesser number of hydrogen atoms. Okay, now let us go for the mechanism of this. Detailed mechanism. Okay. See, propene is treated with HBr. Propene with HBr. Now we'll have two options. Let us first consider H plus Br minus. One way is to go for this. Let this be the first possibility. Possibility A. Let me write what happens. See, it's always from negative to positive. Come on. CH3, CH. Oh, okay. First, let us actually write this way first. Addition is initiated by an electrophile. Let me just add H plus first. I'll be left with this. This becomes CH. So it's a 2-degree carbocation. 2-degree carbocation, of course. In this case, the 2-degree carbocation is more stable. The other one, what we get is a primary. So when compared to primary, 2-degree is more stable. Okay. Now to this, let me now add the bromide ion. Okay. We get the major product. So this is case 1. R, the possibility 1, which is giving us the major product according to Markovnikov. Now check out the other possibility. This may even go in a different way as this. Let this be the possibility B. Now coming to this possibility B, again it's the addition of electrophile first, negative to positive. We get CH3, CH2, then this CH2 plus. This is what is called 1 degree carbocation. Now this 1 degree carbocation is less stable when compared to 2 degree. Add Br minus. Okay. Then we get this product, which is minor. Okay. So this is the mechanism of electrophilic addition. So it is going via a more stable carbocation. Whenever there is a carbocation, you'll have, whenever there is a carbocation intermediate, we'll have rearrangement. Okay. Let me give you an interesting example. Okay. Look at this. See, when this is treated with, say, HCl. Okay. H plus, Cl minus. According to Markovnikov, it's better if we get a negative charge here and a positive charge on this. Rather than going for all the possibilities, let me go for this straight away. Now, the addition of electrophile first. Okay. Then we get this electrophile, because to this CH2, I've added H plus. Now it has become CH. See, from this, straight away Cl minus gets attached. If Cl minus is used, just a minute, it has to be from this to this. Now this is what we get. One of the possibilities, I don't say that this is the major product. One of the possibilities is this. Now let us go for shifting, contraction, everything. Now because this has a angle strain, the angle here is 90 degrees. We can of course overcome that strain going for ring expansion. Come on, very interesting. Now look at this. Cut it here, go for this. Now here, see, the bond is between these two carbons. Look at what happens. See, this carbon is still having its bond intact, whereas this carbon has lost its bond. So let me put a positive charge here. Right. Now this is nothing but a 5-membered ring with say a methyl group and a positive charge on its adjacent carbon, right? Now see, this is a 2-degree carbocation, which of course is less stable, right? There is possibility of this less stable carbocation getting converted into a more stable one. Let me take a hydrogen out. Come on, go for 1,2 hydride shift. Right now, what happens? Okay, then of course we get this kind of positive. Okay, right? So now this is a 3-degree carbocation, more stable. So is going to give us the more stable product, of course, the major product. Now let us consider even this also as it is. If this is considered and if Cl minus is connected, I mean before uh, shifting, if you go for this, or else let's do this way. Okay, we'll use this. As it is, the 2-degree carbocation, though is a less stable, is taken into consideration, we get this methyl group, which is already there. Here it is the Cl. Now go for this Cl minus. Now this Cl minus attacks. What do we get? Final. This along with the chlorine. So this is the major product. What we get? Okay. So this is very interesting. So we get 3 products. First one, second one, and the third. 3 products. Let me give you one more example. Okay. So this is the question. And the interesting part of this is where to generate the positive charge and the negative charge in case of this double bond. You need to be little cautious. Check what I'm going to do. Let me take it this way. Negative here, positive here. See, I've taken this way because the plus M effect of oxygen, plus M, positive mesomeric effect, will of course come to the rescue of the positive charge and stabilizes that, isn't it? Plus M stabilizes the carbocation. This is where you have to be very cautious. If you generate a negative charge over here, then that of course gets destabilized. Always try to have something releasing at the carbon or at a position which has got a positive charge. Here you got a positive charge and try to have something releasing so that the positive charge gets stabilized. If there is a negative charge, try to have something which is withdrawing. Negative means excess. So withdraw. Positive means deficient. So give it. That means you need to have something releasing. So plus M stabilizes the carbocation. This is the logic to be applied. Now it's of course very simple. Come on. Negative. Initially this. Of course, even this also. Go for both at a time and write the final product. What do we get? Okay, bromine here. That's it. So this